And somebody may or not have heard he passed away yesterday. So just wanted to kick off our workshop with a lot of adrenaline and a lot of energy, and I'm pumped up now. I don't know about the rest of you. Welcome. And first of all, I want to apologize for yesterday. We had a few technical glitches, and we got about halfway through the workshop, and I'm just overwhelmed. I'm a little emotional right now because I'm overwhelmed. We had over 400 people who were attempting to get into the workshop room. And so we did break the internet. We crashed the system. So today we've got a couple of safeguards to hopefully prevent that from happening again. We have a limit on the room, and so don't fret if you're trying to get into the room and you get rejected. There will be a recording of these workshops now. Yay! So that was a good thing that came out of it. Yesterday we hadn't planned on recording the workshops. We are recording them today and tomorrow, and then also we are replaying the hour 1 workshop on Friday. We will have another workshop on Friday morning at 9 o'clock, so I can finish what I started yesterday. We can talk about the relational queries, and we can talk about normalization and wrap up our relational realm. So with that in mind, everyone, thank you for being here, and let's proceed. We have a lot to talk about in a little bit of time here. So I'm going to go ahead also during this presentation, and I'll take my camera down so that you can have a little bit better view of the code and some of the slides and everything else involved there. So I'll be back later for questions and answers, and I will be here narrating these slides, of course. So let me just take my webcam down just for now. So welcome to hour 2 of our workshop agenda. We have the ROXIE Realm today. Once again, my plan for this workshop was to dive into areas of ECL that may not be visited that much. The relational realm, the ROXIE realm, and the new machine learning realm, particularly regression. So we're going to be looking at that tomorrow. But today, I wanted to talk about ROXIE. And we have classes in ROXIE. We have 2 classes called ROXIE ECL. And again, we have a lot of people who maybe feel because they work in 4 every day that they don't have a need for ROXIE and may not have a use for the ROXIE training. But there is some great stuff to talk about there, and to talk about kind of the end game, like all that work that we do on the front end, ingesting data, and all that work that we do with preparing the data and getting it ready. And then, well, let's take it to its final conclusion. Let's take it to the load aspect of the ETL, the extract, transform, and load. So this morning, we're going to look at the ROXIE architecture and terminology very quickly, how ROXIE works. And then I'm changing the narrative a little bit. We're going to talk about the things that you use more often. In other words, when we were putting this workshop together, we often started out in simple indexing and talked about the fetch function. But we want to talk about things that the ROXIE developers use every day, and namely those are payload indexing, and then we want to focus on half-key joins, although in our journey through the realm, we'll also take a look at full-key joins as well. And then we'll look at beyond the realm at the end of this workshop. We'll be talking about interfaces, limits, superkeys, package maps, and then open the floor for a Q&A. All right, so these slides are duplicated for your convenience. We do have a training cluster that's up and running this week from 7 a.m. to 7 p.m. This is the URL. I showed this slide yesterday to demonstrate on the ECL IDE how you can connect, or if you're using VS Code, how you can set up your launch JSON entry to connect to that cluster appropriately. Also, I put it in the public chat. Also, in the landing zone of this cluster, you have available for download all of the PDFs, and there is a mod file that you can then download, also import into your repository. And also, not shown here on this slide, there's a zip file, a Community Day 2020 zip file for those of you using VS Code. All right, on to ROXIE, everyone. So here is ROXIE. ROXIE was, first of all, 20 years ago when HPCC first came out, the first cluster of HPCC, as you all know, was Thor. Thor was designed to hammer the data and to process billions of records. And in general, the idea behind Thor back then was to use Thor to build indexes. And so these indexes had been around since the dawn of time, since the dawn of big data, and we were building indexes, but delivering them to other types of delivery systems that I don't want to get into right now. But safe to say, after a couple of years, it was decided that why not use the same kind of technology, the distributed data technology that we use for Thor, and design another cluster to run side saddle in the HPCC system, and we named it ROXIE. And ROXIE originally was named after the creator of the cluster, Richard Chapman's idea. So it was Richard's online XML interface engine. As we went open source, we figured out nobody knew who Richard was, so we changed that acronym to say Rapid Online XML Interface Engine. It's also known as the Rapid Data Delivery Engine. So ROXIE itself is a data delivery cluster. It's configured a little differently than Thor, well, a lot differently than Thor. Let's put it that way. First of all, where Thor is a single-threaded operation, ROXIE can deliver queries concurrently. Actually, every ROXIE node is ready to receive a request from the outside world. Every node then is load balanced. One node can do the job one time, the next query request, another node takes over, and so on. So it's concurrent, and each node has up to 30 threads on that particular node. So with that in mind, the cumulative production ROXIE of 100 nodes, we can then deliver queries 15,000 per second approximately. I used to say 12,000 doing some mathematics, and then John Berger said, kind of chuckled at me and said, we're actually a little bit faster than that. So ROXIE is designed to be read-only. It loves to work with special data sets called indexed data sets. And once again, it distributes those indexes accordingly across all the nodes in the cluster in something that we call data channels. And I already mentioned the concurrency. And the other thing that's important is all queries that get copied or published to ROXIE are pre-compiled. And that's also what makes them very fast, because then the user is just passing parameters to that cluster. The server then reads the request and then contacts the agents on the cluster to deliver the appropriate data from the appropriate data channels. The server then correlates and collates the information, does any post-processing that's necessary, and returns it back to the requester. The example on this slide shows a 5-node ROXIE. All right, so we talked about the ETL process all the time in ECL, the extract, transform, and load. And this, when I talk about ROXIE in my training classes, I like to call this the load process. And again, the load process involves building indexes, deploying data inquiries to the ROXIE cluster. Once again, Thor is used to build the indexes. Again, I like to talk about HPCC kind of like a big data McDonald's, where the people behind the lights, the grill people, are Thor, and they're building the indexes, getting all the data ready. And ROXIE is the person working at the counter, serving you that individual request that you had for data. Indexes built on Thor can also be tested and run on not only Thor, but also HTHOR, although they are eventually designed for their final destination, which is ROXIE. When an index gets built on Thor, again, it divides it into physical parts, just like a normal data set, where you have 400 different, if you had a 400-way or 400-node Thor cluster, you'd have 400 different physical parts, but then you'd have a 401st part, which we like to call the key of keys in the ROXIE realm, or what we like to also call the meta key. All right, so more about that. Let's go to the next slide when we talk about how ROXIE works. All right, so there's my little ROXIE dog doing a search in the beach, and ROXIE has 2 processes on every node. It's called a server process and an agent process. The server's job is to accept the queries and return the results back to the requester. Also combines results from multiple agents. The agent itself stores the individual data on the channels that's, again, linked to the meta key on each server, and delivers the data to the server on demand. So when someone sends a request to a ROXIE cluster, the server process waits for the request. When it's received, the server then reads the meta key, determines which agent has the appropriate data, and sends the portion of the query to those agents, and then waits for results. And then the agents do their thing, returns the data back to the server collates, performs any additional post-processing of that request, and then returns the result set back to the requester. All right, now ROXIE again runs a query by basis of the meta key, using that meta key information. And by the way, meta key is again that part that's stored on, well, we'll talk about this, but it's stored on every single server on the ROXIE cluster. Every single node, I said server, but every single node on the ROXIE cluster, the meta key is stored. We'll talk about how that happens in the next slide. The information of the meta key tells which data channels to send the request to the agents that hold the relevant data. And by the way, there's all kinds of redundancy built into ROXIE, so that if one agent is busy delivering data, then another agent steps in and then takes that data and returns it back. One agent from each channel will respond to the server with the information requested. And the agents on each channel automatically coordinate between themselves automatically to ensure that the exactly one responds to the particular server. Now, how do we make this magic happen? How do we get our work that we do in Thor, the indexes that we build in Thor, the queries that we write in Thor, how do we get them to ROXIE? Again, we don't spray data to ROXIE. The only place we spray is into Thor, of course. So we have a process that's built into HPCC called publishing, also known as deployment. And essentially, there's two ways that we can publish queries. The first way, of course, is by using the built-in interface of the ECL Watch, which I'm going to demonstrate in this workshop. Also, you can use the command line interface. You can use the ECL command line and use the publish option of the ECL command line to publish your queries. All right, and then we're also going to mention at the end of this, we're going to talk a little bit about package maps as well, which handles the data side of the queries. We're going to be looking at that. So the idea behind publishing is we publish the query to ROXIE. One of the servers receives the pre-compiled query, and then any other information that the query needs, which includes library files, physical location of the data, and physical location of the index file parts. All that gets passed to ROXIE via the publish operation. It's very quick too, a parallel copy operation. Sometimes it's so quick I didn't think it worked correctly. But I'll publish a query and I get the green bar that says it's been published successfully, and it's very quick. The server then, once one server gets the query from the publish operation, it automatically then begins a process of multiple copies to other servers in the cluster. So every server then will get a copy of the query, and then once the cluster is aware of the query, any server can execute it on demand. It's really kind of a cool process how that works. All right, so that's the architecture behind ROXIE, and now let's talk about the reason that ROXIE was created and to some extent why we built Thor. And it all involves indexes, delivering data to our customer in a fast searchable format. And we're going to be talking about two types of indexes in this workshop. We're going to first talk about payload indexes, which is the one that you're going to use more often than the second type of index, which we call non-payload, for lack of a better name, or standard indexes is also used to describe that. Payload indexes contain search fields plus extra fields that are stored directly in the index. Non-payload indexes only contain the searchable fields. So payload, the advantage of payload indexes is the fetches, the I/O. It's only one I/O necessary to get all of the data that you're looking for. Where in a standard index, it would have to first grab the searchable fields and then a record pointer, which I'm going to mention, which then goes back to the original data set to pull the rest of the information in. So the advantage of payload index is better performance because of less I/O, but at the expense of disk space. You're going to have redundant data. You're going to have multiple payload indexes that have duplicate copies of names and addresses and so on. But in this day and age of modern technology and the memory that we have, payload indexes are the way to go. Why do we have to have standard? Why is standard indexes even there in the first place? Well, the answer to that is payload indexes do have a size limitation. And that size limitation is approximately, we talk about 32K compressed format. The biggest indicator of whether or not your record structure will be allowed in a payload index is the compiler itself. If you try to build a payload index and the size of the record structure is too large to fit into the payload index, the compiler will give you an error, and then you'll have no other choice but then to redesign your indexes to use a non-payload and a standard index, and then apply a fetch back into the main data set. All right, so let's start talking about the thing that you're going to see the most in ROXIE, and that's payload indexes. So the index statement defines a payload index using 4 parameters, essentially, an optional 5th parameter of options. The first parameter, base, shown here with the red bouncing ball, is the record set for which the index file is going to be created. The second parameter, called def here, is the record structure of your searchable fields. The third parameter is a record structure of the additional fields not used as the search fields. And I'm going to show you all kinds of practical examples in this workshop. Then, of course, the name of the file. So when you build an index, just like building a data set on the cluster, when you build an index data set, it will be stored in a file on originally on the Thor cluster and then later published to ROXIE. Then there's other kinds of options here: sorted, preload, compressed, distributed, a lot more that you can look at in the main index documentation. I'll be honest with you, I keep my ROXIE queries simple. I haven't had a need to do any of these special ones yet, but I know what they're used for. Like preloading, of course, would be if you're running a query multiple times in the same ECL file. Preload keeps the data in memory so it doesn't unload and reload and unload and reload and unload and reload with every call to your query. So there's options here that you can explore, and sometimes you need to use them, but in general, the ROXIE binaries, and thank God for Gavin Halliday and Richard Chapman and stuff, they make my job so easy, and there's very little tweaking that I have to do once I understand the mechanics behind query publishing. All right, so the index statement for a payload, here's an example of a vehicles data set, and where search fields are state and city, and then the extra fields that they're bringing along is last name and first name, and there's the name of the index. Now, interestingly enough, a lot of people that work on Thor, a lot of responsibilities that they have are just to create indexes. And so they'll create indexes on Thor, they'll let the ROXIE team know that the index has been built, and then the ROXIE team goes out and does a remote copy, copies those indexes, and then proceeds with the index design on their end. So a lot of times people just build indexes on the fly. So that's what this build statement is. Build is an action that will actually create the index file that's designated by the build statement. In this example down below, we're building from a vehicles data set, and there's, again, our search field, state and city. Payload field is last name, and then the name of the index shown accordingly. Really, the way I like to do things is I like to define my index first in 2 slides past, and then I like to build just the index definition. So once again, here's a name key using an index, and actually this one is actually using a non-payload index here. We'll get to that one, and then we're going to just build the name key. All right, so that's the idea behind this. But build of an index definition works on both payload and non-payload indexes. All right, so it's time. It's time to test the technology here. Let's all strap in and see how this works today. We're going to go out to the ECL IDE right now. So I'm going to share my screen, and I'm going to just open up the ECL IDE. The first thing we're going to take a look at is a very, very simple payload example. So I'll just wait for my ECL IDE to pop up on our screen here. There we are. So, folks out there, you remember yesterday in hour one, I talked about we were going to take a journey through the realms of relational and ROXIE and regression using a single data set. And again, this data set that I chose was called property. So yesterday we talked about relating property to people and tax data. We actually had a chance to build it before we lost the feed. But today we're going to take the property definition, and we're also going to take the property data set, the property denormalized data set, and build indexes on that. So by the way, just a little housekeeping here. You can see on the left side of the repository, this is the module file that you will import into your repository if you haven't done so already. There's a root file, a root folder, excuse me, called code that has people and property and tax data, and then also the denormalized data set that we created yesterday called people all. And I'll review that in just a moment. And then each folder talks about each day of the workshop. So we have the relational folder, we have a ROXIE folder that we're going to look at today, and then tomorrow we're going to be diving into machine learning and regression. So here's file underscore property, and then yesterday we actually denormalized people and property and tax data together. And what I'm showing you right here, again, here's the denormalized format of what we built yesterday, where we had property and tax data, and then property and tax data combined with people. What I want to show you in this file right here is we also created a second data set, and I want to talk about this. Since the dawn of time in HPCC, every time you create a file on the cluster, the file would automatically create a virtual field called file position. And this field is always there, whether you're generating an XML file, whether you're generating a CSV file, a Thor file, JSON file, there's always an extra field that's there called the virtual file position. It's called virtual because it's not really required in your record structure for operation. It's just there. And if you expose it, like I'm showing you right here, then you can use it. So the naming conventions of this data set using the word plus means that I'm using the base fields of my denormalized data set, plus I'm adding the virtual file position. And the reason I'm going to use that is in the fetch example that I'm going to show you, where the fetch example, once again, if you have a non-payload index that only has search fields, there has to be some way of going back to the main data set to get the rest of the information. And we use the virtual file position to do that. All right, so I am going to first show you the property search service. And well, look how simple this query is. It's almost laughable how simple this is. And again, I want to start simple, and then we'll build up into something a little more challenging. But this one is just a filter on a payload index. That's all this is doing. It's wrapped around a function, passing in a last name key and a first name key to do the search. I have a simple if condition here that simply says if the first name key is blank, well then let's search our payload by last name only. But if the first name key is not blank, then let's search our payload key by last name and by first name. All right, so the base key here is referencing something in a file called IDX and a definition called base IDX. Let's take a quick look at that. Here's the base IDX right here. And this is our first payload index that I'm showing you. I'm referencing the denormalized data set. It's going to be so cool when you see this query. The denormalized data set, searching by last name and first name, and then the payload fields is every other field in that denormalized data set. So I'm just referencing the record structure. Here's the cool thing about this index design is that I don't have to If I had 30, 40, 50 fields that I wanted as payload fields, I don't have to mention all of them individually. I can just reference the record structure. The compiler's smart enough to say, okay, you're using last name and first name as your search fields, and so I'm going to include all the other fields except for last name and first name. So that's how easy it is to design the index. Now, your code that you're going to copy is going to have a triple X here. So if you want to practice building indexes and playing around with ROXIE, the only thing that I would ask you to do is just to put your initials in there. You can see I've put my name in here to distinguish my indexes. Now, this is an index declaration. It's just saying this is what I would like to have on my machine. This is the index that I would like to build. Of course, the follow-up to this is I've got a small little BWR file that then actually goes ahead and builds the index. And the cool thing about these indexes is you can actually look at them and you can see their results. You can actually see their data sets. They're just data sets that have this meta key information built into the header. And there you see I've got a last name and a first name sort here. So yeah, the indexes are looking pretty good and ready to roll. So after I go into my search service, I go in and, well, here we go. How do I get this query to ROXIE? It's a three-step process. Step number one is you change your target to ROXIE. Now, I have chosen in this example to use HTHOR because I wanted to test building my indexes over and over again. If you publish it to HTHOR, then it will not lock the file if you're using a single dolly. So I can test it, and it's actually a good thing. It's actually good too before you actually run through and test it on a real ROXIE system, is to give your queries a test on HTHOR. Why HTHOR? HTHOR is a single-threaded Thor, and it will emulate ROXIE more efficiently or more correctly in reflection than just using Thor. But sometimes you want to publish the Thor because of the size of the data set and what you're going to be also doing in ROXIE with that large data set. So step number one, change your target. Step number two, you compile the process. After you compile the process, you go right into the ECL Watch interface through the IDE. Or if you're using VS Code, you can open up the ECL Watch and go right into that work unit. And then to move this query to ROXIE, we have the publish option. So there's options here that I talk about in our advanced ROXIE class. I'm just going to talk about, setting the job name correctly here. And you'd hit the submit button. It will go ahead and publish this query. I've already published this. I'm not going to do it again. I've already published this correctly, so let's take a look at that. But hitting publish, you'd see a green bar come across the ECL Watch work unit, and then it would verify that you've had it published correctly. I'm going to stop sharing the ECL IDE for just a second. Hopefully this will work out fine. And now I'm going to jump over and share my ECL Watch screen. All right, and we have liftoff. So in the ECL Watch screen, we have this, looks like an LED diode or something here. It's called Published Queries. And here's all the queries that we have published for this workshop. My colleague Hugo is over in the other room right now talking all about ROXIE in Portuguese. And so he's got some published queries there that he's going to be showing you. And then I've got my queries right here. Well, let me just show you the one that I just talked about, which was the search service. And this is a new interface. For some of you that haven't seen this yet, the new interface of the published queries allows you to get to WSECL directly through this ECL Watch instead of using the old method of the 8002 port. You can still use the 8002 port to get to WSECL, but WSECL also is now visible through the published queries interface. And I can type in Spock again, and let's just do a quick search here. And bingo, there is Spock. Now, the cool thing about this payload index, check it out. You got not only all the people involved here, but then you've got all the property of the people and then all the tax data information of that person in a single payload index. So my simplicity of filtering this payload index gave me a very rich and robust result of properties and tax data and everything else that I want to look for here, which is kind of cool. I like it. And I'm excited about it. I was very excited the first time I built a payload index on a denormalized data set and was very happy with the results of its ability to read nested child information very simply, very easily. All right. So that's the first example. Let me get back over to my presentation here. All right, where's my mouse? There we are. All right, so let's move on to our next slide. So we'll take a quick look at standard indexes and then build and fetch again. Standard indexes are, again, payload indexes minus the payload. So you have the index with the base data set. You have your record structures. There is something I do need to mention here. A standard index requires that you add the record pointer, that virtual file position that we discussed in that previous slide. Virtual file position gets added directly to the index so that when you have your search fields, it will then be able to go back and pull in the rest of the information as needed. So you see here, I've got this vehicle files plus, the index is referencing vehicle files plus. The file position field is added as the last field of your non-payload index. There's the name of the index file. So real quickly here, you have the build statement, again, building a standard index on the fly. But then again, I like to build the definition of that index. So we can take another quick peek at that. Before we do that, let's talk about how we use the standard index to go back to the main record set to get the rest of the information. It's done through a function called fetch. Fetch has two parameters at the front here, the base record set, the original set of records from which the index file was built from or created. The index base record set is then the second parameter here, the index file that's being used by the standard index that you're referencing, of course. And then look, the third parameter of fetch has to be that position field. That position field has to be in that index file. By the way, another thing to mention about fetch is a lot of times people talk about, well, filtering my results. It's bad practice, maybe not an efficient practice, to filter the base record set. You almost always want to filter on the index file. Let me show you a quick example of that. Very, very simple example of using fetch. Here we have a function that's passing in a social security number. The fetch statement is fetching from a file header plus file, and the index file is a header key based on social security number. We're simply filtering on the value that's passed in, so the fetch will only return the information that matches the social security number that is being passed. Fetch has the option of also calling a transform, which works exactly like a project. So you just use the left keyword and you can do additional transformation of the fetched results before returning the result back to the ROXIE requestor, the customer. All right, so once again, our first venture into sharing screens was good. Let's try the second venture here. Let's go back over to my ECL IDE again. All right, and our second example that I want to show you here is the one using fetch. So very similar to the search service, with the search service just being a kind of a filtered read of the payload index, the fetch service here is actually reading and then doing the fetch, because the read of the index is only going to give us the searchable fields, the last name and first name. This index, this standard index, is only referencing last name and first name, and then the record position. The record position, which was declared back in the file underscore people all. So there's that record position. We pull that record position over into my index. I build the index using the build statement, and then the fetch service then can then fetch from the base data, the original people all file, the denormalized people file, the filter that I'm dropping in from this filter definition, which was then saying I'm going to filter this way by last name, or I'm going to filter by last name and first name if they pass in a first name to the fetch. Once again, I compiled this. So let me stop sharing my IDE again. Let's take a ride back out to the ECL Watch. All right, fantastic. And now let's just go ahead and close that property search service. We'll look at the fetch service, which, by the way, was pre-published to ROXIE to save time in our workshop. And again, here's our test pages. And by the way, this test pages, look, you can test the SOAP interface, JSON interface, WSDL. A lot of ROXIE developers will ask for the WSDL of your query so that they can consume it into their development system and then wrap it around some pretty web page or some pretty Windows program. You could test the request and response schemas and sample request and sample response schemas and so on. So this is really blown up here in version 7 of HPCC. Our legacy form, once again, is just like the old WSECL. Once again, if we search for Spock, okay, it did the fetch, and again, the result looks exactly the same. Once again, it fetched back to the main data set. Here's all the property information. Here is all the tax data information. All right, cool, cool, cool. And let me stop sharing the ECL Watch. And now let's take this home. We're going to talk about, again, the most commonly used development method of ROXIE queries is the half-key join. And its little brother, the full-key join. We'll take a peek at that. But full-key joins, I'll say right from the start, are really only used when you cannot use a payload index. So a full-key join gives you the ability to go back and do an internal fetch via the join. Now, joins, yes. So all of you out there remember what a join is, of course. A join is taking a left record set, a right record set, a condition of those two record sets, and then what type of join. That would be inner, left outer, right outer, full outer, left only, right only, full only, 7 types of joins. And so we call the joins of indexes half-key joins and full-key joins. And so, yes, not only can you join data sets together, a left record set and a right record set can be a data sets, of course, and we've done those a million times. ROXIE also likes to join indexes. And so these indexes are reflected in full-key joins and half-key joins. We call it a full-key join because there's actually 2 IOs going on, so that's called full. In the half-key join, we don't need to do that second fetch to get the rest of the data, so it's only gone halfway. So that's why we call a half-key join, and a full-key join, a full-key join. So let me explain. Here's the rule of a half-key join. In your join, the right record set must be an index, and it must be a payload index. If it's not, you have more work ahead of you. Because if you do a half-key join with a non-payload index, the right record set index only contains the search fields, and of course the customer just doesn't want to see the search fields because that's what they're searching for in the first place. So you have to rebuild, you'd have to refetch everything else from the base data set, and it's just a lot of extra work. So half-key joins are almost always used with payload indexes, and if you don't use payload indexes for it, you just have more work to do. So also the payload index does not need to have the virtual field because it's not doing a fetch back into the base data set. The join condition can use keyed and wild keywords. We haven't talked about that yet. We're going to look at that in just a minute. As a matter of fact, I think the next slide. Yeah, we have keyed and wild. These are keywords that inform the compiler that you basically know what you're doing. All right. In other words, keyed and wild keywords are wrapped around a particular field or an expression of fields that are Boolean together. And again, keyed and wild are valid in index filters, but also valid in the join condition of a half-key join. And you're simply telling the compiler that you know what you're doing. In other words, the example down here has 4 fields: F1, F2, F3, and F4. But it looks like the index read is only on F2. So if the index is built with F1 being the primary component, and you say, no, I don't want to search by F1, I want to go directly into F2 and search for that. So here F2 is keyed, that is my search criteria, and wild then is then skipped. So it traverses the binary tree and goes directly onto the leaf, and then makes the search more efficient, of course. So we make the F1 key wild. Is this required? No. If you don't put it in and if I just said F2 equals Hugo and nothing else, then the compiler would give me a warning. It would say, you are filtering on a keyed component where there is an upper key component that's not being filtered. But the compiler will still work. It's only a warning. The compiler will still optimize your search. There's a debate on that. Some people have told me that keyed and wild actually improve the efficiency of ROXIE. They do. Richard says they do. All right. So
they absolutely do, because the whole point here is that when you're using keyed and wild, the binary tree is still used, and it's just fully scanned instead of walked the binary tree, so it can get straight to the individual leaf nodes that you want. However, if you're not using keyed and wild and you filter on a trailing component of the index, then what happens is you get a full table scan of all the leaf nodes in the index, which is basically treating the index exactly like a data set, and that's much slower because every single index leaf node will have to be looked at.
Okay. All right. Thank you, Richard. So again, keyed and wild is then encouraged to use for better efficiency. Thanks for Richard for clarifying that. Okay. And then here's an example of a half-key join. Again, the right record set is using a payload index, the left data set here. All right. Now, it says left data set here, but in our ROXIE training classes, what we actually do is we walk people through the development cycle. We show them how to do a full key join first, and then we walk them into a half key join with a standard index and show them all the extra work that they have to do. And then we say, okay, let's build a payload index now. Let's do the half key join. Isn't that much better? Isn't that a lot easier than what you did with the full key join on a standard, half key join on a standard index? And then to polish it up and make it the best query possible, we actually then create a payload index on the left side. So we have left and we have right. They're both payload indexes, and ROXIE will scream in speed. It'll fly through with speed, and that's the optimal design, the best practice of ROXIE design. Now I'm going to show you the half key join service. I do want to mention before I go out there one more time, the full key join is, again, when you cannot use a payload index. The full key join is good because you can use the standard index with the record pointer, and it will then go back and do a fetch into the right record set using the index that you specify in this keyed flag option of the full key join shown here. So here the join left data set, right data set, but it says, okay, no, my right data set is going to fetch the information via the index. And the rule of a full key join is this keyed attribute on the join then instructs the key field, which is part of this index, must be part of this index, to do a fetch into the right data set using the built-in record position or the file position field that is also contained in this index. So there we have that. So, all right, so let's take a look at my simple half key join example. I had fun with this one because I was thinking, you know, after I showed you how cool the denormalized indexes were working and how cool just by, you know, retrieving the nested child information and so on, and all that stuff that I could do just with a simple payload index. Then I said, well, what would be a good example to show a half key join? So I went ahead and I went back to the original normalized data sets, and I created a couple of normalized keys. I have a normalized property file. And again, remember, normalized is just an entity that doesn't have child information. It's just self-contained. So I have my property data, and here are all my search fields for the property data. I broke down all the address fields from house number and so on. And boy, I'm right on time here. That's my 5-minute warning there. So here's all the fields that I have in my search for this index. The payload is person ID, because I'm going to go back and retrieve the person information from the join. I'm going to be joining my property normalized with my people normalized. And then I said, to optimize this, why not create also a people payload index, which then has the normalized people file. The search field is ID, which is going to be used as the link between my half key join, person ID to ID, and then all the payload fields of the people are then brought in automatically. So my first venture to this half key join looks like this. And I haven't talked about the stored interface yet. I'm going to mention that as we wrap up here. But as you can see here, I decided to allow people to search for anything in this query and any combination of these fields in this query. So they could search for zip code and state, or they could search for house number and street, or house number and city, any combination. So that's what this filter is specifying there. It's going to filter down my property, normalized property, to only those, and it's doing an index search. So, and of course I saw some stuff with house number there, so I wanted to trim all the leading spaces there so that I have an accurate search there for that one. And this was just the first draft of this query. And so the left record set was the payload index. The right record set is a payload index. The condition is left person ID, right ID, and so on. And then I'm limiting my ROXIE result. And I could talk about this for another 15, 20 minutes, but essentially when you switch compilers from Thor to ROXIE, the compiler will look for you limiting your index reads by using either limit or choose N. And if you don't limit or choose N, the compiler doesn't recognize it. It will give you a warning and tell you that your index read is not being limited. Why do we do that? Well, the answer is we don't want to bring ROXIE to its knees. We don't want to do a search that's going to be too broad, that's going to load down ROXIE where other people are searching, and then data channels are so busy with this one query that the performance of the other ROXIE queries starts to drop. We don't want that. So sometimes if you don't put a limit around your index read, the compiler will automatically put a 10,000 record limit on your index reads. So we talk about the limit function, we talk about choose N, we talk about the join having also the ability to limit using at most and limit, of course. So that we talk about that in our ROXIE ECL class. So this is the half key join service. I'm going to show you then version 2 that I did. When I did this, I just did a transform right, which just returned the people that matched my address criteria. And I liked it. I said, okay, that's cool, but yeah, I want to see the address. I want to make sure that my search was correct. So I wrote myself another little, well, in the transform of this half key join, I actually went ahead and built an additional field in my output called composite address. So I'm just taking the house number and the other address information and trimming them and concatenating them all together. All right, so let's take a look at this query in our ECL Watch. All right, and so now this is kind of cool. I'm going to go back into my test pages and legacy form. And I was just kind of playing around. I said, well, let's see how many people live on Main Street. Bingo! And there's the people, and there's the address, Main Street, Main Street, Main Street. Remember, I did choose N. I limited my records to the, well, actually, in this case, I didn't put choose N on this one. I just, the test pages, the WSECL will limit you to the first 100 matches. Okay, actually, no, I stand corrected. It looks like it's going beyond that now. That might be something new, Richard. 146 results, 151 results. Wow, I didn't realize that. Okay, let's try one more. I live on First Terrace, so I'm going to type in 1ST and then PER. All right, and there's a few addresses here that match First Terrace. And again, you can play with this query. It's out there on the training cluster. I've got it published out there. It's called bob.propertypeople half-key join service version 2.1. All right, so we're running, getting near our stop time here, 9:51. I want to open up a couple of floor for a couple of questions. So let me go ahead and just stop that screen and talk about our last slide here, which goes into, well, we talk about the stored workflow service. I have to really talk about this. In my half-keyed query, I had some stored workflow services here. This gives you an interface. It's really critical. I really shouldn't rush through this one. This is a workflow service that allows you to give yourself an interface to the ROXIE query, user interface, so they can enter information, so that if they're searching by first name, I'm going to give a stored workflow service for first name, last name. You can look at the code that's out there. I actually tweaked the stored also. The stored also gives you the ability through the WSECL to format the fields and to sequence the fields in a particular order. Also, for strings that are using the stored workflow service and numerics that are using the stored workflow service, WSECL will give you an automatic entry field. But if you have a Boolean field that's using a stored workflow service, the WSECL will automatically render that as a checkbox, a 3-state checkbox, true, false, or default when you're testing your ROXIE queries. All right, and this brings us to the end of our workshop. The other things that go beyond the realm here that I talk about in the online training, and by the way, we have a remote class scheduled for November, where I go into all of these in excruciating detail. And then there's online lessons that you can take anytime you want, 24/7, 365 a year. The interface support, well, you know, that's an ECL structure that allows you to put multiple parameters into a single interface to simplify your query design, so that instead of putting 30 parameters into a function, you can simply reference the interface that contains those 30 parameters, and then you can reference the parameters as needed. We talk about limiting your index reads. We talk about publishing to remote dollies. When you have a single dolly, you don't want to lock your indexes on that dolly, so you can publish to a remote dolly. And then in the real world, we have super keys and package maps that I talk about in the lessons. I'm sorry I ran out of time to talk about these, but really this is the future. We use super keys so that we can dynamically update queries that are active, and then through super keys and package maps, which is an XML file, using the ECL package map option, we could then activate the package map, and we can add new queries to our package maps. We can then add new files to the queries that are being used by the package maps without disrupting Dolly. So all of this handles behind the scenes. The package maps contain all the queries that are published on your ROXIE query. Like I mentioned, these are all covered in the ROXIE classroom and in our remote training and in our online training.
Okay, Bob, have we got any time for questions?
We are done. Thank you so much, everybody. And let's open the floor for questions. Richard, go right ahead.
I don't have a question.
Oh, you want me to look? All right.
No, I don't see any. There are no questions that I see right now in the public chat. If anybody's got any questions, you can probably just unmute your mic and ask away.
All right, yeah, Franz had mentioned there about avoiding a table scan. You already answered that one. That was good.
Yeah.
All right.
Any other questions? Anybody else? Mr. DeFabia? Whitney? Tabitha? Sergey? Any questions for anybody?
Well, let me say this. We will be hanging around. We'll pop into our expo booths. So if you want to go into and ask a question out there, or even contact us using the emails below here, if something comes up during the workshops, you can then go ahead and email us. There's my email. There's Hugo and Richard Taylor, of course, the always fantastic Richard Taylor, who has been doing ECL longer than I've owned my puppies. Richard,
Bob, thank you for the accolades, but we do have a question about the materials for this workshop. Is there a download for them?
Well, yes, the materials are actually on the cluster. There's the PDFs right on the cluster in the landing zone, and you can just download them right there. If you have any difficulty downloading that material, please email me directly, and I can send you the PDFs via email.
And I did put the link for the cluster into this public chat, so everybody can go out and open up the ECL Watch page and go to the landing zone page for that and download all the materials for the class.
All right. Well, thank you so much, everybody. It's 9:57 right now, and some of you have other things to go ahead and do. We will see you tomorrow, hour number 3, for machine learning and a journey through the regression realm. It's going to be an exciting journey, and I hope to see you all there. Thank you so much for your attendance, and thank you for the Infosys team for recording, and we got through it. Yay! All right, everyone. Thank you so much, and we will see you tomorrow morning. All right. Bye-bye now.